Are there other ways we could approach it? Well, as a matter of fact, there are. There are a couple. I mean, at this point, this is an active area of research right now. But the ones, these two had a lot of traction for a minute, and I think they're pretty interesting, especially skip thought. But they're both essentially variants on word2vec. So in doc2vec, instead of just having as your input the words that are in the sentence, you're also including some kind of identifier for the either paragraph, sentence, or document. And so that's involved in your production. You're also you're capturing at some point the fact that all of these words were in the same sentence. And then skip thought takes word2vec vectors and essentially does the word2vec trick on entire sentences. So it, instead of trying to like reconstruct the surrounding words on either side of a word, tries to predict the surrounding sentences from some central sentence, which seems impossible, but it makes vectors, and they seem to capture the meaning of a sentence in a way that's actually useful. And so it's reasonable to ask, how do we determine that what is useful and that it is actually useful? There's a really interesting paper that was released in 2018 called "What You Can Cram into a Single," I don't know, gosh darn vector, and that is a response to a famous quote that oh my gosh, I forget who actually made it, but the quote is that you cannot stick an entire sentence into a single gosh darn vector, and so this group, which was sort of a mix of people largely from Facebook, they realized that in evaluating sentence representations, we typically use downstream tasks as a way of evaluating them, right? Like we might have like a paraphrase detector, like is this paper a paraphrase of some other paper, or use it as a tool to determine entailment, which means like you have a sentence like the dog is green, like the dog's fur is an odd color, right? Like one of these may require that the other be true, and so their point in this paper is that these sorts of tasks, things like paraphrase detection or entailment, actually require some pretty complex inference. So it's hard for us to tell like what is the sentence actually capturing about this collection of words. Is it capturing? Oh, I don't know. Is it capturing like the presence of a word that like will always like clue you into the to this thing being entailed by the other, or is it is this downstream task entirely dependent on the length of the sentence, and is that somehow being encoded in these words in these sentences? So they proposed this, a set of what are called probing tasks. And they found that these sentence embeddings can actually capture a pretty large number of features. They created these little tasks, and each one was designed to test something. Right? Like one was trying to determine like what they call surface features. Like if we take a sentence embedding, can we then like build a classifier that takes the sentence and says, okay, that sentence originally had 5 words in it. So that would be like a sentence length, or could we take this sentence embedding and determine whether or not a given word was in that sentence? And so they created all these little tasks, and they found that you could actually capture a large number of features in fairly simple sentence representations. So you can capture in a single vector sentence length, word content, reverse word order. Even if you like, I think the most exciting one to me is this last idea of odd man out, where they would take a word from the sentence and like randomly change it to like a word that was not previously in the sentence, and could we detect that this sentence had a word that didn't belong in it? But they also found that the information represented in sentence vectors depends really strongly on a couple of other factors, specifically like the architecture of the model that we build, like what kind of like machine learning algorithm are we using? How do we train this how do we train our data? Like, is it just like co-occurrence, or are we trying to solve like a harder problem? Like, are we telling this machine to predict what sentence follows another one? And then finally, its performance also depends on how you evaluate it. So whether or not sentence embeddings work is really task dependent. And so I'm going to present like what's currently thought, well, currently being like this summer when I was working on it. Like one of the most exciting current sentence embeddings is being used. It's this thing called BERT, which is a bidirectional encoder representations from transformers. And I'm not going to like talk about what that means unless people want to talk after this. But broadly, it's a machine learned model that gives us it gives us a pre-train. They start by giving you like a large pre-trained model. Oh, this is developed at Google as well. They give you a large pre-trained model that you can then adapt to your own task by shunting a small amount of your own data at it with a task in mind. But their pre-trained is based on two things. One, where they randomly mask words, like 15% of the sentence, and then try to predict them. So sort of like what WordDevec does, but it takes, but then it also tries to predict the next sentence. And the most noteworthy of this, the most noteworthy thing here is when you use it, it actually is capturing word order. So when you go to retrieve, when you go to say what is the vector for dog, for example, it actually depends on what the context that it appears in. Like you would generate a different vector for each context. So it gives you a sentence representation that's sensitive to word order, which should be really exciting, and you can fine-tune it to your own task. So what am I doing with it? Well, my own research is funded by a language and autism grant, and I'm currently, like, as I try to finish my my PhD, I'm modeling the flow of topics in a conversation from this autism diagnostic observation schedule, which is like I don't know if you're familiar with it, but it's one of the primary tools for that clinicians use to determine an ASD diagnosis. So one of the things that I'm interested in is this idea of like non-contingent speech. So like when an examiner, in the case of the ADOS, says, tell me about your school day, and the subject replies with, oh, my cat is also very large. So non-contingent meaning that it's not following the topic that's being proposed by the other speaker. So obviously something like this would require a way to represent sentences that includes some sense of their meaning. So you can determine whether or not my cat is also very large when it is not an appropriate response to telling about your school day. So here are a couple of ways that I've applied them on that particular problem. So ADOS conversations are partially scripted. The examiners are given like a set of questions that they're supposed to ask, like what are some things that make you happy, or what makes you angry? And so I created an examiner, like what I call a topic tagger, to identify when a variation of one of those sentences used in the conversation, so we could track, like, without having to do a huge amount of like manual annotation, is there are we now in the section of the ADOS where the child is being asked about happiness versus angriness? And then I'm also working on oh my God, look at that spelling. Working on a model that can determine whether or not a subject speech follows examiner's topics. So in the first one of the features that I use to determine whether or not we are in one of these blocks, like the happiness block or the angriness block, is how similar the examiner's last utterance was to one of the scripted sentences. So what did I use? And this is maybe more sausage making than anyone cares, but like for those who are following along, I'm using the large pre-trained BERT model. I'm using the second to last hidden layer for my representation of sentences. It's not fine-tuned for any task. And I think one thing that's worth thinking about while I show you this next slide is what would be a good task to use to fine-tune it. So in the example where I'm trying to like guess where the happiness section versus the sadness section has begun, is this is some examples of like good and bad similarities. These are each one of these examples at the bottom is the highest is a case where the highest similarity score for, so we're comparing this utterance versus the scripted sentence using a pre-trained BERT model. when the scripted sentence is considered the sentence it's most like, and then the associated similarity score. And I promise this will become more clear in a second. So here's a really great example, right? The examiner says to the child, what are some things that you like to do that make you feel cheerful? So the sentence it's the most like is this one, the scripted sentence, and its similarity to that sentence is 0.94. Which is great. It's what you want, right? It looks similar. It's almost the exact same words. And then we have another positive example, relatively, anyways. Like here's another case where the scripted sentence it's the most like is what do you do that makes you feel happy and cheerful? Sure, it's she jumped up, which shouldn't match anything, and it doesn't. It like just sort of arbitrarily, the closest one is this, but it has a pretty low similarity score of 0.45. So that seems pretty reasonable too. But we also have these cases, if we use the untuned BERT model, if the examiner says, what are the kinds of things that make you feel sad, we get this as the most likely scripted sentence, which is interesting in that, sure, the sentences are similar, and in like a really like naive sense, they even should be considered as similar sentences, right? Like these are both questions about the sorts of things you do that make you feel, some sort of emotion. But what's not being captured is like the valence of that emotion. So one thing that it seems like you could do is you could, as a way of fine-tuning the BERT models, which is what I should have been doing today, but instead I was taking care of my children, is you could train this. You take the BERT model and you then add a classifier where what you're trying to classify it is into one of those sections. Is it the happiness section, the sadness section, or the anger section, for example? And hopefully, that would give us a sentence representation that is sensitive to the fact that we care about the difference between the words sad and cheerful. So for those of you for those of you who want to experiment a bit, I do all of this stuff in Python. I find it most NLP I find, like most NLP researchers do most of their work in Python. That may be a vast oversimplification, but I think it's true. So if you're interested in word-to-vec, so taking words and coming up with a representation of them that is that's a vector that you can then compare and say king plus female minus man equals queen, is that something like that? Then try. I really strongly suggest this GenSim application is a really nice interface for working with word-to-vec. It's really simple. It's got good documentation. But if you want to try like larger sentence representations, I do suggest experimenting with BERT. It seems pretty exciting. I like its tunabilityness. I like that they've thought about what makes a sentence a sentence. The Google research has the pre-trained models here. You have 4 you can choose from. And then to get started with it, there are 2 really easy ways to get started. Well, the first is very easy, and the second one is, I'm going to say it's easy, but it took me days. Which is BERT as a service, which is it's a Python library that you can download. You point it at the pre-trained BERT model, and you can immediately just start. You type in like an array that is a list. Sorry, you type in a list of words representing your sentence, and it will spit out a vector for you. It's really it's pretty cool. And then if you want to do it in PyTorch, so you have more, which is like a machine learning interface for Python, so that you have more control over what's being learned and what sorts of like, well, if you want to fiddle with it yourself, I suggest using this. There's a company called Hugging Face that started, I think, like creating like a kind of like artificial chat app, but now is mostly known for this, their library for building BERT, which is Hugging Face Transformers. And then there's this really great hands-on guide to using that, which is on the Towards Data Science website. But if you just do a search for text classification with transformer models, it will bring you to that. And it starts you with nothing, and by the time you're done, you've actually used BERT to decide what something is, and you've trained it and fine-tuned it. And thanks. If you guys, this is the first time I've ever been to PyData. I'll stay in touch. If people want to email with questions or comments, or just have my email address, it's here. Feel free to email me. Anyways, thanks, guys. I'm sorry if that went over.